Okay, we're going to start with spirometry now. This is the second lecture capture. Let's look at the graph here, and let me take you through what you see. Let's start off with tidal volume right there. And let me get rid of all that. Okay, so for tidal volume, what we have is inhale, exhale, inhale, exhale, inhale, exhale. That's tidal volume. It's your normal volume in and out under normal conditions. It's like the tide comes in, same amount goes out. It's somewhere like 300 to 600. Let's say it's, I don't know, 500 in this example. So 500 would be your tidal volume, 500 inhale, 500 exhale. Now at the bottom of this exhale, where we would normally take a normal inhalation, we're going to do a normal inhalation, but then we're going to keep on inhaling beyond a normal inhalation. This amount right here beyond a normal inhalation is called inspiratory reserve volume, IRV, beyond the normal inhalation. Now we're then going to exhale. So we exhale, then we exhale the regular tidal volume, and now we're going to exhale everything beyond a normal exhalation. So from here to here is expiratory reserve volume. Inspiratory reserve volume, everything beyond a normal inhalation. Expiratory, everything beyond a normal exhalation. Okay, those three numbers, IRV, TV, and ERV, from here to here, that's called vital capacity. So if you take your max amount of air and then you blow it out as much as you can, from there to there is tidal volume. Vital capacity, sorry about that. By the way, in case you're wondering why some are called volumes and some are capacities, capacities are combinations of volumes. Now, vital capacity is this orange-yellow arrow space that you see here. Now, look at this residual volume right here. If you blow everything out you possibly can down to there, you can't get any more out. There's still going to be some air left in your lungs. There's some air left in the alveoli, there's air left in spaces. That's called residual volume. There's no way to measure it. Now if you add residual volume to these three volumes, remember this is equal to vital capacity, you've got total lung capacity, TLC. There's no way to measure that because you can't measure residual volume, but you can measure vital capacity. By the way, the picture that you see over here at the bottom left is a spirometer. We'll be using it in lab to measure expiratory volumes. Okay, you've got a variety of respiratory rates here to look at, just to show you what happens to respiratory rate as you get older. There are two other spirometric volumes and rates that are important. Respiratory minute volume, or sometimes called minute ventilation, which tells you how much air is coming in and going out of your lungs every minute. It's the respiratory rate times tidal volume. So if your respiratory rate is 12, which is low, but we'll use it, and your tidal volume is 500, you got a respiratory minute volume of 6,000. That's about almost 2 gallons of air. Now, just because 6,000 mils is going down into your lungs doesn't mean that all of that is getting down to the alveoli. Remember, there's a lot of area in your lung where the air is just sitting there. The only air that's really important is that gets down the alveoli, because that's the air that can diffuse across the membrane. So that area in your lungs where the air is sitting and not doing anything, it's not being conducted across a membrane, is called dead space. So if you look at the alveolar ventilation rate here, you'll notice it looks very similar to respiratory minute volume, except that it includes something called dead space, which I just defined for you. So the more dead space you've got, in this example I used 150, the less air gets down the alveoli. So if I'm using 150 mils of dead space, look at the difference between that and that. The tidal volume is the same, respiratory rate is the same, but dead space has been factored in. So if you have something like tuberculosis or you have lung cancer and there's a bunch of dead tissue in the lung, the air is just going to be sitting in that dead tissue, that's dead space, and it's not in an area where it can diffuse across a membrane. That increases your dead space and it decreases your alveolar ventilation rate. Also notice, anything that affects your respiratory rate will affect the amount of air getting down into your lungs. So if you're on morphine or some sort of depressant, and your respiratory rate went down to 9 breaths per minute, you're going to have about 4,500 mils per minute of air getting down there. Okay, so some basics in gas exchange. I'm going to take you through a couple of very important laws, and I'll stop this tape and we'll pick up with gas transport in the last portion. Or maybe I should, nah, it's too early to stop. Okay, so some basics in gas exchange. Dalton's law of partial pressures. Total pressure in a mixture is equal to all of the individual gases' pressures added up together. These individual pressures of the gases that are in the mixture are called partial pressure. Pressure exerted by each gas is given as millimeters per mercury. Now let me use this chart down here to illustrate it. Look at atmosphere first. There are 4 major gases in the atmosphere. There are a few other guys, but these are the 4. Now, look at the percentages of these gases. You can see nitrogen is the number 1. If we want to figure out the PN2, partial pressure of nitrogen, we would take the total atmospheric pressure and multiply it by the percent, that's supposed to be a percent sign, of N2 in the atmosphere. Which means the total atmospheric pressure at sea level is 760, and at sea level the percent of N2 is 78.4. And if we multiply this times that, that's exactly what I have written right there. What we get is 596. If we do this for oxygen, we take 760, multiply it by the percent of oxygen. These two multiplied together gives you 160. If you do that for water and for CO2, of course there's water vapor generally in air. If you do that for all 4 gases, here are your P, CO2, P, H2O, P, O2, P, N2. You add them up together, you get 760. Now, look at this definition. The total pressure exerted by a mixture is equal to the sum of all individual gas pressures. Okay, so this plus this plus this plus this equals this, which is the total pressure of the mixture. That's what Dalton's law is. You do the same thing over here in the alveoli. One thing you'll notice right away is that the CO2 level is much higher and the water is much higher in your lungs, and that gives you a much higher pH2O and a pCO2. Okay, we'll talk more about that as we move along. One last thing. Gases will move and diffuse and react according to partial pressure, not concentration. It is partial pressure that's causing gases to move, causing gases to react with hemoglobin, blah, blah, blah. Okay, there's another law, and that is Henry's law. Gases in a mixture will dissolve in a liquid according to each partial pressure and solubility. So, here's pressure. Oops. Back up a minute. I can't get back out of here. Up. Sorry. There. Okay. Here is pressure times solubility coefficient, and that equals the amount of dissolved gas. So, look down here at solubility coefficients, and let's go with O2. There it is right there. It's not important to remember these. But if you take this 0.024 and you multiply it by the PO2, let's say in alveolar air, which was 100, that will give you the amount of dissolved oxygen in your alveolar air. And notice that oxygen isn't all that soluble. It's pretty insoluble. It doesn't go into solution. Look at CO2. It's got a higher solubility coefficient. It goes into solution very easily. N2, not at all. Half of what it is for oxygen. Very insoluble. Now look down here. If we're using oxygen as our standard, and let's say that we make oxygen 1, then CO2 is 20 times more soluble than oxygen is. Which means then, when we talk about transport of CO2 and partial pressures, CO2 is much easier to move than oxygen is because of that solubility. N2, on the other hand, is pretty insoluble. Now this doesn't play much of a factor. Now remember, every time you inhale, you're inhaling 70% N2. Every time you exhale, you're exhaling that N2 out. It goes into your blood, it crosses the respiratory membrane, it's carried around in your blood, but nothing happens to it. It's insoluble. It's a non-issue. Your body is ignoring it, and then you just breathe it out. Now there is one time when that N2 becomes a problem, when it does go into solution. Now remember that here is the key. Pressure times solubility coefficient. Well, think about when pressure goes up. Pressure will become a much greater value when you descend. Now, if you're at sea level, how do you descend? Well, you dive. So, if you go down 33 feet, you're at 2 atmospheric pressures. If you go down 66 feet, you're at 3 atmospheric pressures. So look what's going to happen. You increase that value of pressure, and the solubility coefficient is always going to be 0.012 for N2. But the concentration of the N2 that is dissolved goes up. When you dive, you get more and more N2 in your dissolved in your blood. We'll talk about that problem at the very end. Okay, we've talked about, I think, everything here, so I don't think there's anything else to talk about. And I think that about takes us to gas transport. Yep. Okay, so I'm going to stop here because I want to kind of keep all the transport together.